Hello and welcome. In this video, we're going to talk about sample spaces and types of probability. And our two goals are that we can describe a sample space and its subset, and that we can identify the difference between theoretical and experimental probability. So let's go ahead and jump in. So before we jump into the calculation aspect, let's make sure we're on the same page about the vocabulary. First of all, a probability experiment is an action or trial that has varying results. If I roll a die, that is a probability experiment. The possibilities that could happen when I roll that die, a 1, 2, 3, 4, 5, 6, are the outcomes. A list of all of the possible outcomes is called the sample space. So a probability experiment could be that I'm rolling a die. A possible outcome is that I roll a 2. The sample space would be all the things that I could roll, 1, 2, 3, 4, 5, 6. The probability of an event is the likelihood or chance that it will occur. That is going to be a number from 0 to 1, or if we're speaking in percentages, from 0 to 100%, and including both of those things. So in the example that we just talked about where we were rolling a die, the probability of rolling a 0, if there isn't a 0 on the die, would be 0. The probability of rolling a number would be 1. So it's going to be a number between 0 and 1. It can be expressed as a decimal, as a fraction, or as a percent. So the probability of rolling a 6 would be 1 out of the 6 total options. That would be representing it as a fraction. Some probabilities can also be found geometrically. So if we're given an image and we're asked about probability of something hitting an image, like a dartboard, we'll look at examples like that. But that would be geometric probability, because instead of using the possible outcomes, you're looking at the geometric shape and using area and things along those lines. So this is sort of just a scale that helps you visualize. 100% or 1 would be that it's certain that something is going to happen. If I roll a die, I'm going to get a number. That would be 100%, or a probability of 1, because it will certainly happen. Something being impossible would be a probability of 0, and then you have the various values in between. And obviously this is a number line. Every number in between those two numbers exists, but it's just giving you a visual idea of what this means. So now that we've established that vocabulary, let's talk about theoretical probability and then talk about notation a little bit. So the theoretical probability is basically what should happen, what we would expect to happen based on the math. The way that we would calculate that is right here in the middle. We would look at the number of favorable events, or the likelihood of the event occurring, over the total frequency of possible outcomes. So again, going back to the dice example, we could say the probability of rolling a 3, and this is what that notation would look like. So here we have P for probability, and then in parentheses we have what we're saying the probability of. The probability of rolling a 3, if we think about the dice, there are 6 total outcomes and one of them is a 3. So that's how we would find the theoretical probability of that situation, the number of times it could occur versus the number of possible outcomes. Another example could be something like the probability of rolling an even number. In that case, there's still 6 outcomes, but the even numbers, 2, 4, and 6, there are 3 of them. So the probability of rolling an even number would be 3 over 6, and we always simplify our fractions. So that probability would be 1/2. So notationally, we're looking at something like the probability of an event, or you could define an event to be A. So then you could say the probability of A, again, P, parentheses, and then whatever we're saying is going to happen. There is also the probability of a complement. So in this example up here, we said the probability of rolling a 3. The complement of that would be the probability of not rolling a 3, which is the same thing calculation-wise as 1 minus the probability of rolling a 3, right? The probability of rolling a 3 is 1/6, so the probability of not rolling a 3 would be 5/6. We can calculate that by simply finding the probability of rolling a 3 and subtracting it from the total probability, which is 1. Sometimes it's easier to find the probability of the complement, the opposite of what we're saying, and to subtract from 1. Sometimes it's just as easy to say there were 5 possibilities that weren't a 3, and to calculate it using the theoretical probability formula. We will get into various examples along those lines in this lesson today. So just remember, the theoretical probability is the number of favorable outcomes, or the frequency of the event we're talking about occurring, out of the total number of outcomes. And now that we have that formula and our vocabulary under our belt, let's go ahead and look at some examples. Okay, so for this first example, we're going to go back to this idea of rolling a die, and we're just going to focus on tying the vocabulary and the notation that we just covered to something that I think we're all familiar with. So if you roll a six-sided die, what is one possible outcome for this event? It's possible that we roll a 3. The sample space is the list of all the possible outcomes. So if I'm rolling a six-sided die, I could roll any of the integers from 1 to 6. And then we're going to get into probability. So what is the probability of rolling a number that's greater than 4? The probability that we roll greater than 4, so I'm writing P parentheses, and then inside I'm writing what the event is, roll greater than 4. And then I'm just going to look. We have 6 total options. This is how theoretical probability works. We're going to put the number of options on the bottom and the number that match what we're talking about on the top. So there are 2 of our options that are greater than 4. We're going to always simplify our fractions. And then here on this specific example, they're also asking us to write it as a decimal. 1/3 is the same thing as 0.3 repeating. For the last example, it says greater than or equal to 4. So I'm going to write P parentheses, roll greater than or equal to 4. And now that just means I'm going to include one more number. There are still 6 total outcomes, and now 3 of those 6 outcomes meet the needs that we're being asked for. 3 over 6 is going to simplify to 1/2, and if we write this as a decimal, that would be 0.5. Now let's go ahead and look at another example where we have more than one thing happening at a time. Okay, here we go. Now we're going to flip a coin and roll a die. So the first thing we're going to be asked to do is create the sample space. If you think that you can do that without any help at all, go ahead and pause the video and work through writing out the sample space. If you think you need a little help, then bear with me. The second thing we're going to do is we're going to find the probability of something specific, that we flip heads and roll an even number, and we're going to use that appropriate notation with P in the parentheses. So sample space. When we flip a coin, there's really 2 options. We could roll heads and we could roll tails. And we already talked about when we roll a die, we're going to say this is a 6-sided die. We have the options 1, 2, 3, 4, 5, 6. So one option is that we could flip heads and we could roll a 1. We could also flip heads and roll a 2. We could also flip heads and roll a 3. I think you're seeing where this is going. So go ahead and pause the video and finish filling out the sample space. So hopefully you had enough time to work out that sample space, and here it is now. If you didn't, you can pause the video and fill it out. But I want you to notice there are 12 total outcomes. So when we're looking at the theoretical probability, our denominator in this case is going to be 12 because we have heads and tails, but we also have the digits from 1 to 6 that we could be rolling. So for part B, what is the probability that you flip heads and roll an even number? So the probability that we have heads and even is, well, we know our denominator is going to be 12 because that's how many outcomes. And then what we're going to do is we're going to look up and see how many of our outcomes actually have heads and even. So go ahead and pause the video and just circle or highlight each of the answers that meets both of these requirements, heads and even. All right, hopefully you had time to do that. So I see heads and even only 3 times because there's only 6 options that have heads and 3 of them have odd numbers. So out of the 12 total outcomes, 3 of them are both heads and even, and that's going to simplify to be 1/4. And notice it doesn't say anything about decimal places here, so I'm just going to leave my answer as a fraction that's simplified. So hopefully this is starting to click a little bit more. Let's go ahead and look at another example. Okay, so for this next example, I'm going to have you try to work through it mostly on your own and then check in and follow along with me to see how you did. But before you pause the video, let's read through and make sure we understand and we're setting everything up consistently. So number 3 says a student is taking a 4-question true-false quiz and guesses on each question. Fill in the table below to identify the sample space. So if you're guessing on a 4-question quiz, it's possible that you get 0 correct. It's possible that you get 4 correct, right? And then all the options in between. Instead of writing the words correct and incorrect over and over again, let's actually create a let statement. Let's let I equal incorrect and C equal correct. And here's how that's going to help us. What would the outcome look like if we got 0 answers correct? It would look like incorrect, 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 incorrect. One example of a way we could get one question correct is that we could get the first question correct, and then we could get all the other ones incorrect. Or we could just get the second question correct. Or we could just get the third question correct. And there are more options for each of these. So when you're listing the outcomes, you're going to list the ways or which question number we could get correct for each of these. And that's going to help you find the total number of outcomes. You're going to use those total number of outcomes to figure out the probability of getting exactly 2 answers correct, and then the probability of not getting 2 answers correct, so getting anything besides 2 answers correct. So go ahead and pause the video, finish filling out the outcome sample space, and then see how far you can get on B and C, and do your best to be consistent with the way we have been writing our statements and notation out. All right, so hopefully you had time to work through the sample space. Here is the filled out sample space. There are 16 total outcomes. For part B, we're being asked for the probability of getting exactly 2 answers correct. So I'm going to say the probability of 2 C's. And we know that the total number of outcomes is 16. Of those 16, we want to look at how many of them are 2 correct. So how many of them are in this row here? And it looks like there are 6 in that row. So the probability of 2 correct, or 2C, is going to be 6 over 16. And again, we're going to simplify our fraction. If we divide 6 by 2, we get 3. And if we divide 16 by 2, we get 8. Now for part C, we're being asked for the probability of not getting 2 correct. So getting 0, 1, 3, or 4 correct. And I want to just point out there's 2 ways. So I'm going to say the probability of not 2C. There's a couple ways that we could look at finding this. First of all, we could just count how many are in all of the other columns. So here and here. If we count how many are in the other columns, we're going to get out of the 16, there are 10 of them that do not have exactly 2 C's. And that is going to simplify probability of not 2C. If I divide by 2, I'm going to get 5/8. We could also use that vocabulary word that we learned about complement, and I just want to take this minute to point it out. The probability that we do not have 2 correct is going to be the same as 1 minus the probability that we do have 2 correct, and we already found that number up here. So the probability that we have not 2C is going to be 1 minus 3/8. And instead of writing 1, I'm going to write 1 as 8 over 8 so that I already have a common denominator. 8 over 8 minus 3 over 8 is 5 over 8, and we get the exact same answer here using complements. In this case, it's probably the same amount of difficulty to use complements as it is to just count using the sample space, but we might look at more complicated problems where you really would prefer to use the complement. Here, it's really up to you. Now let's go ahead and look at an example that involves geometric probability. All right, let's suppose that this image here is a dartboard. The question says, suppose you throw a dart at the board shown below. Your dart is equally likely to hit any point inside the square board, the blue board here. And then we're going to be asked 2 questions. Are we more likely to get 10 points or 0 points? And are we more likely to hit 5 points or 10 points? So it sounds like we need to know what the probability of 10, the probability of 5, the probability of 0 are. So unlike the last problems, each of these probabilities are going to be based on area. So if we want to find the probability of 10 points, that's going to be the total area of the 10-point section divided by the total area of the entire dartboard. So let's start by finding the area of the entire dartboard. This is telling us that each of these is 3, which means this length is 9 and it's a square. So the length of each side of the square is 18. So if we want to find the total area of the dartboard, what we're really saying is what's the area of that square? And that's going to be 18 times 18, which is 324. So that's going to become the denominator in our fraction for each of our probabilities. The numerator for the area of 10 is just the area of this reddish pink circle here. So this has a radius of 3, so the area of the circle, I'm going to say the area of 10 points is the area of a circle, which is pi r squared. In this case, pi times 3 squared, which is 9 pi. So the area, let's erase this. This looks like a negative sign now. The area of 10, the 10-point section, is 9 pi out of the total area of the dartboard is 324. And this is going to simplify to be pi over 36. And if we had a calculator, then we could get an idea of how much this actually is. So let me grab a calculator. Pi divided by 36 is 0.0873. That feels like enough decimal places. So again, we're going to find the specific area we need out of the total area. We need to compare this to the probability of 0 points, which is the blue section. So let's find the probability of 0. Again, we know the total square is 324. So what we need to do is find this area if we added all those pieces together. Well, I'm going to call that the blue area. The blue area is the entire square minus the area of the biggest circle. So if you think you can calculate that, go ahead and pause the video and try. But I'm going to walk through this with you because this is our first geometric example. And some of this might be a little rusty. We said the square area was 324. The biggest circle has a radius of 9 because each of those is 3. So it's going to be pi times 9 squared. So the area of 0 is 324 minus 81 pi. So the probability of getting 0 points is the total area of 0, which is 324 minus 81 pi. That's the area that takes up the 0 point spot on the board, divided by the total area of the board. Now, each of these, we can grab a calculator, but let's first simplify. Each of these three numbers is divisible by 81, and if we do that, we get 4 minus pi over 324. Now, if we're going to compare this, it seems like the probability of 0 is going to be bigger, but let's grab a calculator. Let's type 4 minus pi, hit equals, divide that by 324. That's going to give us 0.215. So this is obviously bigger. We want to make sure that we clearly answer our question. So what we're going to do is we're going to write a sentence answering the question. That sentence is going to say, we are more likely to hit 0 points than we are to hit 10 points. For part B, we already know the probability of 10 points. We have that here. So we need to figure out the probability of 5 points and then figure out which of those is greater. So 5 points is just this green circle. So we need to find the area of the full circle that has a radius that's 6. And then we need to subtract the area of the pink circle. But let's go ahead and set this up. And again, if you feel confident, I encourage you to pause the video and try on your own. But if you want to work through this with me, that's great. So the probability of throwing a dart and hitting 5 points is the total area for 5, area of 5, divided by the total area, which is 324. So I'm going to come over here to do my work for the area of 5 points. Well, this circle, I already said, has a radius of 6. So it's going to be 36, 6 squared, pi r squared. 6 squared is 36 pi. But we want to subtract out the pink or the red part of this circle, which we already found that area to be 9 pi. So the area of the green, 36 minus 9, is going to be 27 pi. So the area of 5 points is 27 pi. We're going to divide that by 324. We're going to simplify our fraction because I always want us to practice doing that. So both of these are divisible by 27. That would give us pi over 12. And then we can grab our calculator. Pi divided by 12 is going to be 0.261. And then we're comparing these two numbers. And obviously, the probability of 5 is greater than the probability of 10. So we're going to go ahead and write a sentence that says, we are more likely to hit 5 points than 10 points. So it's incredibly important to me that you not only have the math that validates that your answer is true, but that you're clearly answering the question that's being asked here. So we have our sentence and we have our mathematical proof of the sentence, the computation comparing those two numbers. Okay, we're going to look at one more theoretical probability example, and then we're going to move into experimental probability. All right, when two six-sided dice are rolled, there are 36 possible outcomes, which are shown so you don't have to create the sample space. I'm going to encourage you to pause the video and work through example 5 on your own, and then unpause the video and see how you did. Then we'll move into our last topic for this video. So hopefully you had time to work on part A. The probability that the sum is not 6 is 1 minus the probability that it is 6. And there's only 5 places that it could be 6. So the probability that the sum is not 6 is 31 out of 36. You also could have simply counted how many didn't have 6 instead of counting how many did. Similarly, the probability that the sum is less than or equal to 9 would be the probability that of 1 minus the sum being greater than 9. I'm using the complement here. So that would be 1 minus 6 over 36, which is 30 over 36, or 5 over 6. So hopefully this theoretical probability is starting to make more sense and you're feeling more confident in your computations. Let's talk about experimental probability. If theoretical probability was summarized as what should happen, we all know that what should happen isn't always what happens. I should roll a 6 every 6 times I roll the dice, but it's totally possible that I roll the dice 12 times and I don't roll any 6s at all. And that's the difference between experimental probability and theoretical probability. An experiment is that process of actually repeating a trial. So experimental probability is probability that is based on the experiment. The number of trials would be your denominator, like how many times I roll my die versus how many times I successfully accomplish whatever the thing is that I'm trying to find the probability of. So experimental probability is basically based on data. A lot of businesses and companies make decisions based on experimental probability or experimental trials because they're using that data to drive the decisions that they are making. Let's look at a couple quick examples and then wrap up this video. Suppose we have this spinner, and I'm going to tell you that each of these 4 spaces has the same area, so it's equally likely to spin an A, a B, a C, a D. But we spun the spinner 20 times, and here are the results. So find the experimental probability of spinning A. Well, the experimental probability of spinning A, so probability of spinning A, is how many times we spun A out of the total number of times that we spun, which is 5 out of 20 or 1/4. Why don't you go ahead and pause the video and find the experimental probability of spinning A or B, and then unpause the video and see how you did. Hopefully you had enough time to do that. Of the 20 spins, 14 of them were either A or B. 14 out of 20 can be simplified if I divide by 2 to 7 over 10. Now, part C says, for which letter is the experimental probability the same as the theoretical probability? So if I didn't have this table here, if I just had the spinner and I said, tell me the probability of spinning an A or a B or a C or a D, that probability would be 1 out of 4 because they're taking up 1/4 of that space. So if we look back at part A, so I'm going to say based on part A, the probability of A is the same theoretically and based on the data from this experiment. All right, last example. In the United States, a survey of 2,184 adults found that 1,328 of them have a pet. So this is the number that have pets. The types of pets that they have are shown in this figure, in this graph to the right. So part A is asking, what is the probability that a pet-owning adult, so that means that knowing that they have a pet, they have a dog. So knowing that they have a pet means that our denominator should be the total number of people that have pets. So how many of those people own a dog? So looking at this table, that value in the numerator should be 916. And then as always, we're going to simplify this fraction. These are both divisible by 4. That's going to give us 229 over 332. Last but not least, what is the probability that a pet owning adult, so again, we're starting with knowing that they own a pet, owns a fish. So probability that the pet is a fish. Knowing that they own a pet makes the population or the denominator 1,328. Of those 1,328, 146 of them own a fish. And then this fraction is going to simplify to 73 over 674. All right, let's wrap up this video. All right, that's a wrap on 1.1 sample space and types of probability. Our goal in this lesson was that we could describe a sample space, so we could list the possible outcomes, and that we could describe the difference between theoretical, what should happen, and experimental, what did happen, probability. So make sure you write down any questions you have, and I look forward to supporting you on this. Thanks for listening.